So this is called an oriented directed graph. So there's something from each. Only directed edges are flowing out of it, and there's another one that's just receiving. So, and then like the flow is always, sorry, this one's the other way. The flow is always in this, like in some direction. So you don't have any arrows going both ways. Alright, I guess, yeah, you don't have cycles either. Alright, so then you can think of the weights as the capacity. And, well, this, so how much capacity it can have. But if you have like some physical systems, then the energy it allows to go in has to match what goes out. So we want to figure out what are the numbers we can put in each of these edges that satisfy that all the flow going into a node is also the flow going out of it. And we want to maximize it. So pick the biggest numbers we can. Alright, so for example, something that satisfies the flow here, if you just put zeros everywhere, it satisfies that everything going in is the same as everything going out because everything is zero. But we want to pick the biggest numbers we can. This is a classical problem in computer science, so there's a ton of solutions. Just like with sorting, we've seen like 4 different types of sorting, maybe more. With this one, if you look at the wiki page, there's like more than 10 different algorithms to do this. And we're just going to look at one of them, okay? And so this algorithm is in, it's described in lecture 7C. So it's a Moodle lecture 7C. That is the same PDF that describes Dijkstra's algorithm. And yeah, I guess Kruskal is described in 7B. So I think it's just Dijkstra and Max Flow are in that one. Anyways, so how do we solve this? So the idea is that we're going to have the flow graph over here. And at the beginning, it's just the nodes. I guess I'll just imagine it with zeros everywhere. So it's the same graph, but the numbers are zeros. So far the only thing I can guarantee is that I can put a flow of 0. And then I'll have my residual graph. And it's just going to be this graph, and then I'm going to keep adjusting it. All right? And what you're going to do, so I'm too lazy to write it again, but it's this graph. All right? So you copy this graph here, and then what you're going to do is you're going to do Dijkstra's algorithm on it. So you start here, So this one is value 23, 17, 41. You can't get from S to D, so this is infinity. You can't get to C, you can't get to T, you can't get to A. All right, so you put infinities where you can't get to. This one is 0, right? Okay, and then of these numbers, the smallest one is 17. So this one is locked. And now I start scanning out from B. So 17 plus 15 is 32. And 17 plus 20 is 37. And those are all the places where there's an outflow from B. So now I look at all the numbers again and I pick the smallest one. That's 23, that's locked. Now I start scanning from F. 23 plus 24 is 47, that's bigger than 32. So 32 is not changed. Now the numbers written, 32 is the next smallest one. And I start scanning from A. 32 plus 56 is 88. 32 plus 25 is 57, which is bigger than 37, so this is not changed. So now I look at all the numbers, the smallest one is 37, so now I start scanning from C. 37 plus 31 is 68. And I could keep going with Dijkstra's algorithm, but it turns out that it's unnecessary because what I need to do is get a path from S to T. Since I already looked at what happens when you're scanning from the two things that map to T, I don't need to keep going. You could keep going, but it's not necessary. So now we know the path to get to T, right? It's here, here, here. All right? So in this path, the smallest number is 17. So 17 is smaller than 20 and 31. So what I'm going to do is I go to my flow graph and I change the zeros in the path to 17s. Okay? And now my updated residual graph will be, you go from S to F, that's 23. So what happens is that now instead of 17, now it's a 0 here. So in the places where I did the path, I'm going to subtract 17 from all of those. So 17 minus 17 is 0. So to make analysis easier, I'm just going to ignore it. When I get to 0, I'll delete it. Okay, so you have this graph. Again, what happened was this guy got deleted. 20 minus 17 became 3. 31 minus 17 became 14. Okay, so now you do Dijkstra's algorithm here. So
If you're missing one in that one from Z to B.
C to B?
Or
Oh,
D
D
to
to
B.
B, right? And that one is 15. Okay, so let's see. So this is 23, that is 41. So I scan from here. Sorry, this was infinity, 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 infinity. So this is now 47. 41 is the smallest one, so now I scan from here. This becomes 65. This becomes 61. And the smallest number now is 47, right? So 47 plus 56 is 103. 47 plus 25 is 72 maybe? So the next smallest one is this one, right? Okay, so from 61 plus 15, 76 is bigger than 65, so no changes. 61 plus 42 is bigger than 72, so no changes. So that's it. So now 65 is the smallest one. 65 plus 15 overshoots. 65 plus 3, we get 68. So now this one we circle. 68 plus 14. This one became 82. So the shortest path includes this, I guess it's this guy. It's like this. So now in that path, the shortest edge is 3. So we add 3 to everything in that edge. So we use this one, 0 becomes 3. We use this one, 0 becomes 3. We use this one, so you add 3 to 17, you get 20. And then you add 3 to 17, you get 20. So the flow graph is now this. Alright, so now what happened to the residual graph? This edge is going to be deleted, right? So we draw it again. Now the residual graph is this one stays unchanged. 41 minus 3 is 38. E to B is 21 now. F to A stays the same. A to T stays the same. T to C stays the same. C to T goes down by 3. E to D stays the same. D to C stays the same. E to A. Okay, so now this is the residual graph. I guess I'm missing this one. So the B to C guy got deleted. So now you do Dijkstra. There's probably a way to draw it all in the same graph all the time. But if I keep drawing in the graphs, it's a little easier to do the Dijkstra part. Alright, so 23, infinity, 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 38, infinity, infinity. Alright, you scan from S, we're done. 23 is the smallest. You scan from F, this is 47. That's the only change. Now this is the next smallest. You scan from E, 38 plus 21 is 59. This is 58. That's it. 47 is the next smallest one. This one is 103. This one is 72. That's it. The next smallest one is 58. 58 plus 42 is bigger than 72. 58 plus 15 is bigger than 59. So no changes. This is the next guy. 59 plus 15 overshoots it. So now we go here, and 72 plus 11 is 83. it looks like the path is 23 plus 24 plus 25 plus 11. And that's the shortest path from S to T. Now, in this path, the edge with smallest number is 11, right? 11 smaller than 25, 23, and 24. So, on everything in that path, we add 11. So, 23 is now, sorry, 0 is now 11. This is in the path, yeah, 11. And then A to C is 11. And then C to T is 31. Okay? All right. So then the next stage is we're going to subtract 11 from all of these guys. So I'll just do the drawing here. So 11, so this one is erased. Let's see, so we subtract 11 from 23, we get 12. We subtract 11 from 24, we get 13. We subtract 11 from 25, we get 14. And this edge got deleted, right? So the residual graph is this. We do Dijkstra again. All right. So we have 23. Infinity, 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 infinity. No, this one is 41. So the next smallest one is 23. When you scan out from here.
Isn't that one small?
Yes. Thank you. That one's 12. When you scan out from here, this is 25. And because there's no path from C to T, it's actually easy to see that this is already maximized. So that path is here, here. You can't do better than that. The only way to get to A would be this, which is too costly for like that, which is cheap. I guess you could also do this, but that's even more expensive. So, of these numbers, the smallest one is 12. So you add 12 here, add 12 there, and you add 12 here. So, is it fine if I just make the changes in this one, or you want me to redraw it?
I think you have to erase BC though. B to C.
We used B to C before?
Well,
On the
it's-
second one.
yeah. That was the cheapest one on the second one. It's not on the left though.
Oh, it shouldn't have been here. Yeah, good point. Thank you. Yeah. So that one is not even there. All right. Okay, so I'll just change this. So the 12 was this. So this goes away. At some point, the graph is simple enough that you don't even need to use Dijkstra anymore to find the shortest path. You can just use your common sense. All right, so this number changes to a 1 because we subtracted 12, and this one changes to a 44. Okay? So that's the residual graph. There's no way to get to F anymore. Oh, sorry, there's a path from here to there, which is 31, so there is a way to get to 34. At some point I forgot to include it, so there's a 0 there. Well, maybe when I drew the graph at the beginning, I didn't have that.
Yeah, it wasn't there at the
Oh, it wasn't there, perfect, then we'll just ignore it. Give us a little easier, a slightly easier graph. All right, okay, so we have this. This wasn't there, so I won't put it back. All right, so the original didn't have it, right? I didn't draw from B to F, is that right?
Yeah.
Good. All right, so we can't really reach F anymore. So the shortest path to T, it must include this guy. So this has to be there, right? Because you can't reach T otherwise. And you can't really use F. So you have to arrive to A somehow. So you have to arrive from here. And now we just need to figure out the cheapest way to get to B. So you could either do 41 plus 24 or 41 plus 20 plus 15. Clearly, 41 plus 24 is the cheapest. Right? So now we add 15 to all of those. So we add 15 here. We add 15 here. We add 15 here. And we add 15 here. And that means this number is reduced to 26, this number to 9, this gets deleted, this number gets reduced by 15 to 29. And now in the residual graph, there's no way to get from S to T, so we stop the algorithm. So, so we get this, and this is the answer, the max flow for that, for the original graph which I deleted. And you can check that, so if you're here, 23 flows in, 23 flows out. If you're at A, so the number flowing in is 15 plus 23, which is 38. And the number flowing out is 11 plus 27, which is also 38.
That's cool.
If you look at E, flowing in is 18, flowing out is 18. If you look at D, flowing in, flowing out, oh, so this should be a 0. If you look at B, the things flowing in are 17 plus 18 plus 0, which is 35. If you look at things flowing out, is 15 plus 20, which is 35. If you look at C, flowing in is 20 plus 11, which is 31. Flowing out is 31. And if the other rule that it has to satisfy is whatever flows out from the origin has to be what flows in. So flowing out 23 plus 17 plus 18, which is 58. And 31 plus 27 is 58. So this algorithm will give you something that satisfies the flow, and it's supposed to be maximum. Okay, so this one, you need to be able to do this by hand for midterm 3 and for homework A.
You're gonna give us a nice simple graph in the midterm, right?
Yeah, that one in the midterm, probably, maybe. So how many vertices is this? 8? So maybe something like 6 vertices, something like that. I mean, technically, you don't need to use Dijkstra to do it.
Can you just use?
At some point, you can just use common sense to figure out the shortest path. Probably at the beginning, when you have the original graph, it does make sense to use Dijkstra to not mess it up.
My shortest path is the least weight path. Or literally.
And Dijkstra, yeah.
Okay.
So that the sum of the
Yeah.
path is small.
Not necessarily the least number of edges.
It's not about the least number of
Yeah,
edges,
okay.
it's the least weight.
If
Yeah.
you get too small, like, for the visual graph, if two edges are the smallest and they're equal to each other, does it matter which one you do with the two front?
Sorry, what was the question again?
Like, you know how we go through a path of resistance in a visual graph, and then the smallest edge we delete off of the graph? What if there's two of them, like, they're equal?
You delete both of them.
Both of them?
Yeah. Because you subtract that value from every edge, so those edges become zero, so you can imagine they're not there. Yeah, now, so when you do Dijkstra, sometimes you have a choice, right? The shortest path is not unique. And you can imagine if all the numbers are the same, if all the numbers are the number 5, then as long as you have two paths of the same number of edges, then both of them will satisfy the material. So yeah, sometimes you get to have a choice, like so whenever there's a tie, right, when you're changing this number and you're like 59 plus 15 is bigger than 47, so I don't include it. But what if it were a tie? Then you can actually change your path. You know, grab that other path. So, like if you have like the shortest path from A to C, you could pick this or you could pick that, and they're both correct. Right? So if you're doing the flow problem, then, well, so if you're doing if this is S and this is T, and when you do the flow problem, if you first pick this as your smallest flow, then the answer will be I think this works. So from S, the flow out is 7 and 3, and the flow in of T is 7 and 3, so they both add to 10. And 3 flowed in, 3 flowed out. So that's what happens if you pick this as your shortest, then you're going to delete this. So then the shortest path is this, and then you do a 3, 3. Right? But if you pick this first, then this guy is deleted. And you want the shortest path from here to there, so that's 7. Anyways, so this one, you get two paths, right? So if you're trying to solve this with this algorithm, then let's look at the residual and the flow. So if you pick this as your shortest path, then the residual will be this, and the flow will be that. Okay? So then in the next stage, the shortest path is 3, 4. So the residual changes to just 1 with no path from S to T, and the flow is 3, 3. So here it's 0, 0, then it changes to 3, 3. But if instead of picking this one, you pick that first, you would get 3, 3, 0. Sorry. No, the residual would be 1, 7, and the flow would be 0, 3, 3. And then after the next stage, you get nothing drawn here. You're just left with that 1. There's no path from S to T. And the flow is. I mean, this is a tiny graph, but you can see sometimes the shortest path, you have more than one shortest path. Just pick one of them. At the end of the day, you will get the same answer. So that the steps are different, right? This here you put the 7 first, and then the 3, and then the 3, 3. Here you put the 3, 3 first, and then the 7. But at the end of the day, you get the same graph. Any other questions? Oh yeah, the other thing we saw was topological sort. Yeah, I think you also have to do that in homework 8. Yeah, so at the end of lecture 7C, there's this maximizing network flow problem, and that's what we just did. So S is for source, and T is for sink. All right. Yeah. All right, so this took less time than I thought it would, so we can get back to the matrices. All right, so a reminder on the matrix problem what we're doing last class. So the goal was to do the least number of operations. So we did an example where we're multiplying 4 matrices. What if we're multiplying 10 matrices? Now, for this to be even valid, then the number of columns in the first matrix has to match the number of rows in the second matrix. Let's use different ladders so that it's less, so that it matches the lecture notes. So really you have only n plus 1 numbers that represent the number of rows and columns of each matrix. So di is the number of rows in AI and number of columns in AI minus 1. This is for I between 2 and then plus 1. Well, and then. Okay, yeah. D1 is the number of rows in A1, and Dn plus 1 is the number of columns in An. All right. want to figure out the number of operations. Required to compute A1, A2, A.8. So that's the goal. So there's a ton of ways of figuring out how to multiply these matrices. There are Cn-1 possibilities. This happens to be 1 over n. There's 2n-2, choose n-1. Or how to multiply these matrices. So it's not feasible to do this. You can't just check all of them, compute how much each one of them takes, and be satisfied with this is how you do it. It's just too many possibilities. So we're going to try to come up with the optimal thing. All right, so let's just do it with notes. So suppose you have the product from A1 through AN, and you look at the last operation you did. And the last operation, let's say, was between AK and AK+1. So if that is the last operation in your optimal structure, that means that you had to do the optimal one here and the optimal one there. So you get a divide and conquer sort of situation. You can optimize this and optimize that. Then now you know how to do the whole thing. Alright, so the fact that it breaks down this way suggests we can use a divide and conquer approach. Divide and conquer things usually are recursive, right? And recursion's a good idea to attack them is using dynamic programming. Alright, so all right, let's do an example of how to do this. So let's have a 5 by 2 times a 2 by 3 times a 3 by 4 times a 4 by 6 times a 6 by 7 times a 7 times 8. And we're going to build a matrix M, where Mij represents the number of multiplications in the product Mi times Mi+1 times Mij. So we have this thing, and we pick subsets in it. And we're going to figure out all the ways to multiply from one moment to another. Okay? So when you get a matrix, whatever the matrix is at the end, this lower triangle will all be zeros. Right? First of all, because you can't multiply backwards. So for this to make sense, j has to be bigger than I. If j is less than or equal to I, then Mij will just be 0. So a lot of it you can just fill out right away. Okay, so then how do we do this? So let's do this example. How do we get that matrix? All right, so yeah, we have time. So let's look at A1 was 5 by 2. A2 is 2 by 3. A3 is 3 by 4. A4 is 4 by 6. A5 is 6 by 7. A6 is 7 by 8. So we're trying to build this matrix. It's going to have 36 entries. Because we have the product from A1 through A6, so there's 6 rows, 6 columns. All of these are zeros just from this rule. But now this diagonal is going to be relatively easy to do because this number here is the number of operations in A1 times A2, which is 5 times 2 times 3, that's 30. The number here is the number of operations between these two guys. So that's 2 times 3 times 4, which is 24. Here we get 3 times 4 times 6, which is 72. And then we have 4 times 6 times 7. 168 maybe. And then we have 6 times 7 times 8. 336. Is that right? Feels right. So those are easy to fill out. And you can see those are the numbers I have there on the top. 30, 24, 72, 168, 336. But that's easy to do because we're just multiplying two matrices and we know what's the optimal there, right? Okay, now what do we do here? So A1, A2, A3 could be A1, A2 times A3 or A1 times A2, A3. Well, we know how much this costs, 24. So this number here would be 24 times, so it's the minimum of 24 times so I think the relevant numbers are these. So 24 times 40. Or if you grab this as 30 times 60. So clearly this is smaller, right? So the number that goes there is 24 times 40, which somehow it's not 64. So that's because it's not times, it's plus. There we go. The minimum of 24 plus 40 and 30 plus 60 is 64. Okay, now this one is hard to do because I'm going to need the number here to build this one. So for this one, I needed these two. For this one, I'll need these two. But I can do this with a similar way as I computed that. What I can do is, so this number here is A2 times A3 times A4, which is A2, A3 times A4, or A2 times A3 times A4, right? So I get, this one cost me 24, and the operation from here to there would be 2 times 4 times 6. Over here I have 2 times 3 times 6 plus whatever this number is, which it looks like it's 72. So this comes out to 72, and this is obviously bigger than 72, so the number there is 72. Yeah, all right. So it looks correct. So basically you can just go in order and fill out this matrix. And each one of the operations just use the numbers you have computed so far. It gets a little trickier eventually. Because I think you need more spots. Okay, yeah, it's not so bad. So the recurrence relation is that the entry in the ith and jth position. Oh, okay. Yeah, it does get pretty bad. So you just have a big sum. So you add 3 things, but you check for all things beyond a certain point. So the examples we've done so far only needed to check 2 things, but once I want this guy, I'm gonna need to take into account all of these numbers. And I'll do a minimum calculation there, find this. So there's a recurrence, that's this guy here. And so the coding is a little subtle, but you just go in order, compute a diagonal, and the next diagonal, and the next diagonal until you're done. And once you're done, you get this number. And to compute each part of these diagonals, you're doing a recurrence relation. So this is useful to do with dynamic programming, so that you store the things that you're putting in the matrix as you're going. Because you're going to need to compute them many times. So you just compute it once, and then each time you need it, you call it. All right. Have a nice weekend. I'll see you Monday.
Do you know if there's food at the talk today?
What?
If there's food at the talk today?
Is there a talk today? Oh, yeah. For those interested in the financial talk, there's a talk today in Tarble at 4.
At 4, isn't it at noon? Your email
At
said
noon.
noon.
At whatever time I said in the email. Yeah, I don't know when it is.
Do you know if there's food?
Cybersecurity, but the people working in the bank. Yeah, cybersecurity talk today at Tarble.
Do you know if there's food?
It's at noon?
Yeah.
I would think so. I mean, I would think so, but I'm not 100%.
Do you give participation grade?
No.
No.
I'm not gonna be there.
You're not gonna be there?
That's finance.
Wait, then I'm not gonna be there.